Hi, I'm Ben-Yaakov. This is a continuing education lectures. It's an English version of a series of lectures that I've been giving at Ben-Gurion University to some technical people there. This is a part one of lectures about MOSFET datasheets. Let me say a few words about the style of this lecture, the approach that I've been taking. Normally, the education courses are arranged in sort of a top-up arrangement. First of all, there is the basics courses like mathematics, physics, etc., some intermediate, and then eventually we get into the application. This will be a typical engineering program. Now, what I'm trying to do here is really to start from the top. That is, start with a data sheet of a real transistor, and then go into the reason why we have these parameters, how they originate, what they're doing to the circuit, etc., etc., so as to find details of all the meaning of these parameters. So this is the idea behind these lectures. I'm starting with this particular MOSFET datasheet of IXIS. No endorsement implied here. This is just an example that I've picked up. There are many other vendors that manufacturers that are making transistors of the same type, well, not exactly the same, but of similar type. So this is just an example for an arrangement of a data sheet and the parameters of this data sheet. So there's nothing specific about this unit that I'm be discussing here. So the first page of a data sheet, very typically, will have, first of all, of course, the name or the catalog number of the element, and in this case, this is the number. Actually, there are two different designations, and these are for different casing. We'll talk about in a second. And in this particular case, IXIS is actually giving some hint of what is this device. This is not always done. In some cases, you have a number which says nothing. Here we say 120.65, which means that this is a 650 volt device with 120 amp and this is 24 milliohm. This is the resistance while the transistor is on. We'll talk about it later, of course. Now, very typically, we are going to have here some general description. It's an n-channel enhancement mode, which means that the transistor will conduct when you have a positive voltage on the gate. Avalanche rated and fast intrinsic diode. We'll talk about it later. And here is a sort of a symbol and just a hint what's inside. And we see that there is a MOSFET transistor plus a diode. Now, this is a intrinsic diode. It's not something that is attached. In fact, when you buy a MOSFET transistor, you sort of get a package deal. You get a gift, this diode. As it turned out, in many cases, this diode is really causing a lot of trouble, and we'll talk about it later on. But you can't get rid of it. That's it. Once you get this transistor, you get a diode with it. Now, we have here two cases. One is the 264, 274. These numbers are actually according to the EIA. EIA stands for, let me see here. This is EIA Standard, which is the Electronic Industry Association, which sort of sets up standards for various things. Among them are casings. And in fact, there is, of course, a detailed description of this casing. Now, what it says here is the designation of these, the connection of these terminals here, these pins. This is the gate, source, drain, and tab. Now, tab is underneath. There is actually a metal plate here and here. And the purpose of this metal plate is to transfer heat from inside this transistor to preferably a heat sink that you would attach, and we'll talk about it, of course, in detail. So this is the casing, and as I've said, there is a description of this casing here, and these are the exact dimension, tolerances, etc. I'll not go into it, which are important, of course, for the mechanical design of a piece of equipment. Now, in the first page, you'll also find some description of like recommended application, features, etc. And these are not really parameters, not specifications. This is just a way that the vendor, the manufacturer, is trying to tell you where to use it and, of course, why it's so good. For example, it has an international standard packages, low QG, we'll talk about it, avalanche rated, and low package inductance, which is important. But these are not real numbers of parameters. This is just a sort of, I'd say, advertisement, and the vendor is trying to sell you this particular. It's useful. Let's not forget about it, but it's not something that you can rely on. You should rely on what is inside these tables. Okay, now typically we are going to have tables as shown here, starting with maximum ratings. We'll talk about it in a second. And then there are some other tables, etc., and related subjects like the diode and characteristic of the diode. And we're going to have graphs which are added information to the table. And the tables are really abiding. This is sort of a contract between the vendor and the buyer, and says, here, this is what this device is supposed to do. And if it doesn't, you can just put it back in the package, send it back, say, sorry, your device is not standing behind these datasheet parameters. So this is like a, you might say, a contract with the manufacturer. So let me start with the maximum rating. This is the first table, very important, although these are not operating conditions. These are just parameters that tell you that you should not exceed these, otherwise the device might be damaged. Okay, so this is the parameters, and let's have a look at the first one, which is this VDSS. Okay, well, what does this mean? Well, I have to go back for a second. Here it is. Okay, that's better. So VDSS means that you connect actually the gate and source and impose the voltage here. Okay, this is this meaning of VDSS. You connect these two together. And what it says under these test conditions, very important to look at the test condition. This is really a very important piece of information. It says that up to 650 volts, this device will not be damaged. It can withstand this voltage. And then it also says that if you put this will be the second line here, 1 megohm, here it is, between gate and source, and then impose this voltage, is 650 volts, it'll be also okay. Now this is important because in some cases drivers might have high impedance, so high resistance at the output. Well, not 1 megohm, but it could be high. And suddenly it might have some leakage so that the impedance is high. Now, if there is a sort of a conduction path between drain and gate, this may turn on the transistor. So by this parameters, we understand that we have a safe situation in which even high impedance here will not be affected by the voltage imposed, or it's a electric field between the drain and the gate. Okay, so that's for the VDSS. Let's go now to VGSS. Now, we understand now that VGSS would mean that you connect the drain to the source and then you feed a voltage here. And what it says is that this particular device will withstand a continuous plus minus up to plus minus 30 volt and a transient of 40 volt. Well, it's not that nice that they are not specifying what is a transient. They should have given information saying, well, lasting at least that long. But anyhow, this means that a spike, short spike of a 40 volt will not damage the gate. Now, the point is that this information is very important, and the parameter is very important, because a transistor, a MOSFET transistor, a very, very general description, here, will have a channel, source terminal, a drain terminal, there is insulation here, and this is the gate. This is here insulation. Now, if you exceed these values, there'll be a short in this insulation, and that's the end of the transistor. Now, this could be a very short pulse, and in some cases during transient phenomena and maybe some radiation from other units, you may have imposing a high voltage here. So this is something to worry about, and you have to be very careful that the impedance of this point in the circuit, when you connect, say, a driver or any other circuit, the impedance here will be low, so that this point will be kept at a controlled voltage and not be affected by some connections, by some source here that will, by say capacitive coupling, inject some noise in here. Okay, so we got this one, we got this one, so let's go to here. Now, what this says is that the ID 25, which means 25 degrees, is 120 amp. That is, you can pass through this transistor 120 amp. That's quite impressive for a device of this size. And for a short time, you can actually pass 240 amp. Limited, but TJ max is the maximum junction temperature. We'll talk about it. So this device, as we understand now, can tolerate 650 volts and 120 amp. Now, you would have thought that you can connect this device, have here 650 volts, and pass 120 amp. Well, if you do that, what you're going to see is the smoke coming out. The reason is that these are not to be imposed together, and each one of them by itself is okay, and the combination of them is causing heat dissipation, okay? Power dissipation. And power dissipation is voltage times current. Now, in the case that we are talking about, 650 volt times 120 amp is what? Is like, I don't know, about 70 kilowatts. That's a lot. That's impossible for a device like this to dissipate and transfer the energy. So there is a limitation about the amount of power that this device can handle and transfer to the output, because it cannot leave this heat in itself, because the temperature will go very high. And we'll talk about it in the relevant parameters. So let's just remember that these are just parameters, each by itself. Now we move to another parameter, which is kind of something that has been added in the last, 10 years, and that is the avalanche information. And it says here that the IA, the avalanche, is at 25 degrees, is 15 amp, and that the energy, maximum energy involved, is 3.5 joule. Okay, now what is it? The thing is that in some application, you might encounter a case, I'm talking about the situation that the gate is actually at low voltage. Of course, the transistor is off, and here you have momentarily a high voltage above 650 volt, that is higher than that. Now, as it turns out, modern transistor, power MOSFET transistor, are built in such a way that they act like a Zener diode. Okay, a Zener diode looks, this will be a Zener diode of about 650 volt, so that once the voltage goes above it, then it'll clamp it to about 650 volt, which is fine. The point is, of course, that this cannot be sustained forever. And what this parameter says, that as long as the current will be less than 15 amp, and the energy less than 3.5 joule, then this will be okay. Okay? So let's do a short calculation here, and that will be the following. Suppose I have now a pulse, and a current of 15 amp is now fed to the drain, since I've exceeded the maximum voltage. And my question is, how long can this be tolerated by this transistor? And to do this calculation, I use this equation that energy, or joule, is volt times Q. Q is the charge. And Q by itself is the current times delta T. So delta T is this joule over V times the current. And let's erase it. So this is 3.5, 650 times 15. So this is the time that this device can tolerate 15 amp when it is in the avalanche mode. How much is it? Well, this is about 10,000, 3.5, 10 to the minus 4. So this would be 350 microseconds. Okay, that will be the time that this device can tolerate this current. Okay, so I hope we understand this, and then we move to the next parameter, which is the power dissipation. And it says that this device can dissipate 1,250 watts, 1.25 kilowatts. Wow, that's really very nice. But there is a catch here. And this is something that sometimes, I'd say many times, overlooked. The catch is that it says, well, you can do that provided that the temperature of the case will be 25 degrees centigrade. Okay, So what does this mean? For that, I have to go into the question of thermal modeling of a device like that. Okay? So let me go to a clear sheet here. And let's do the following. If you have the transistor, here it is, and this is the connections, source, drain, and here's the gate. Here's now the plate. This is the tab that you have at the bottom of the transistor. This is the case. And heat is generated here. Okay, let me just emphasize here, that's heat. And this heat has to move out somehow, because if not, the temperature will go up very high. Now we have a model to describe this process. It is basically very similar to Ohm's law. Go back to black. Here's the junction. This is this point here. Now we have thermal resistances and a voltage source. In this model, power is current, and this R thermal is this resistor, and temperature is voltage. So here I have actually the ambient. This is ambient. And let's assume that this ambient is 25 degrees centigrade. By the way, this may not be the case in many instances, because if you have some equipment, a power supply, there is a heatsink here. Here's the transistor. The temperature within the power supply is not 25 degrees. It could be like 40 degrees, depending on the design, okay? So then you might have another resistance between here and the ambient, okay? The 25 degree or whatever your room temperature is. So let's assume that we went all the way from the junction to... Now what are these resistances? These are the thermal resistances in units of degree centigrade per watt between the junction and the case, between the case and the heatsink, and between the heatsink and the ambient. As I said, assuming an ambient here of 25 degrees. Okay. Now we're going to see, of course, the parameter, this parameter and this parameter are given by the manufacturer. By the way, in this particular transistor, you have junction to case. There is some resistance between case and heatsink, but on many instances, you would put between the transistor, this is now the metal part of it, and the case, insulation. The reason is that this case is connected to the drain. Okay, here's the transistor, this is the drain, and this part is connected to the drain. Now normally, this drain is high voltage. It's not ground. And therefore, certainly not for a p-channel transistor, or n-channel transistor. So, in this case, you cannot connect it to the heatsink if the heatsink is at ground temperature. And you'd like to keep it at ground temperature. You don't want this heatsink to be all at high voltage. So therefore you put some insulation in here, which adds another resistance. So I'm not talking about this for a minute, because we really don't need it here for our discussion. Let me just erase the stuff that I don't need. Okay, so we got all this get rid of, so it'll be less clogged here. So now let's go back to this parameter of 100, 1250 watts dissipation. Where is this number coming from? It turns out that from junction to case, this is 0.1 degree per watt. So if the current, which is power, is 1.2 kilowatt, then the voltage drop or temperature drop will be 125 degrees centigrade, because it is 1.2 kilowatt times 0.1. Now, if this point is kept at 25 degrees centigrade, then you add 25, you got to 150 degrees centigrade, and this is the maximum permissible temperature of the junction here. We'll see it. We haven't seen it yet, but it is in the data sheet, believe me. So this is from where this number is coming from. The question is, of course, can we keep this 25 degrees at the case? Well, obviously, if the ambient temperature is 25, you want this to be 25, the thermal resistance between this point, that is the case, and the ambient should be 0. In reality, this will be a much, much larger number, certainly not 0. How much will it be? Well, let me erase this. When we have the transistor, as I've said, first of all, we have the 0.1 degree per watt between the junction and the case. Then we have between the case and the heatsink, and assuming there is no insulation here, no insulation, okay? This turns out to be like 0.1 or let's say 0.15 degrees centigrade per watt. And then we have the heatsink. And eventually we go, and I'm assuming the ambient of the heatsink is 25 degrees. Make it easy for the transistor. Now, what is the thermal resistance of a heatsink? Well, a regular heatsink will have, like a 10 by 10 centimeter and say height of 2 centimeter, okay? So it's a heatsink like this. We would have something in the area of say 2 degrees centigrade per watt. Which means that with 1.2 kilowatts, the drop will be what? Unbelievable. 2000.4 degrees Celsius. Fantastic. Now, the best you can do with a heatsink for such a transistor today, using a fan here and a very large heatsink, maybe you can get by with 0.2 degree per watt. Okay? Now, 250 watts times 0.2 is 250 degrees centigrade. Way too high too. So what can be done? Well, the only way would be to use some other means of cooling. If indeed you try to keep this slab here at 25 degrees centigrade. For example, you can use liquid cooling. Pass a cool liquid through some heatsink for liquid, attach it here, and then lower by this actually the ambient temperature. So you have a larger permissible temperature drop. The bottom line is that this number of where are we? This number here of 1.2 kilowatt is just not realistic. I mean, this is really way off. And again, it just comes from this parameter of junction to case of 0.1, okay? Which is just the beginning of the story, and that's not the end of the story in terms of the thermal conduction. Okay, let's move on now to the next parameter, which is dVdt. And this parameter, here it is, tells us the following. Well, again, let's have a look at the condition up to 150 degrees, voltage not exceeding VDSS, of course, and let's stop here. And the point is that if the voltage at the drain is rising very fast, there might be a problem. And this is actually limiting this rise to 50 volt per nanosecond. And let's say that we have a converter. And for that purpose, let me sort of have a look at a boost converter. Okay? What is a boost converter? We have an input, we have an output. This is the load, this is a filter capacitor, transistor, and what basically we're doing, we are turning this transistor on. It is charging here the inductor, and then we turn the transistor off, and this current is then passing through here to the output. As we turn the transistor off here, the voltage that is at the ground side when it is on, because there is actually a short here, will start going up. This is what we are talking about. Now let's assume that the output is 400 volt, which is very typical of, say, a power factor correction circuit. And we have a span of 400 volt, and we are allowed 50 nanosecond, 15 volt per nanosecond. So 400 volt is like 8 times this, which is 8 nanosecond. This is what it means. So it says that you should not go faster than 10 nanosecond for this span here. Well, the question is, why? What's the problem here? Well, the problem is that you have internal capacitances in the device. And if this goes very fast, then you inject here charge carriers, and therefore the transistor might turn on and eventually break down. So this is a limitation, but as it turns out, it's really not a severe limitation, because rarely will this voltage go that fast. Well, the reason is that this transistor, and we're going to see it later on, has some capacitance. That's not something you put in. Again, it's like the diode, something that you're getting, C out SS. We'll talk about it later. And due to this capacitance, if you have a current going into a capacitor, there is a limit to the rise of the voltage. So you will normally not exceed this thing. So this is a warning. This is really a sort of a nice warning, but normally you don't worry about it. Okay, now we move to the temperature. This is the maximum temperature allowed of the junction, and it says that's between minus 55 and 150 degrees centigrade, and that the maximum is 150, and that the storage, this is storage temperature, is also the same thing. This is, by the way, not necessarily so. Always there are some devices that would have a operating temperature says till 120 and storage 150. So, but this is just an information that is very, very important, because thermal issues depend on this. And you have to be very careful not to approach 150 degrees. That's very dangerous, because that's a breakdown. Now we have another temperature-related parameter. That's the maximum lead temperature for soldering. Here, when you're soldering, this is getting hot. The heat goes inside and may damage the device, the chip. So it says that this should not be more than 300 centigrade, and also that if you are at a given distance and heating it up, you are allowed to have 260 degree, 160 degree, for 10 seconds. Okay, so you have to do it quickly. Don't hesitate, and just touch the pin for with the iron, soldering iron a long time, because this could actually damage the device inside. Okay, the next parameter we're going to talk about is the torque, and the point is here that these devices, let me go back to the actual data sheet, here it is, do have mounting holes that you put some screws in to hold it to the, go back to the to say the heatsink, okay? Then you have a screw here that you put in here. And it limits the torque that with the screwdriver you force to this value, it's a Newton meter or pound per Newton meter or pound inch, and this is like 1.13 Newton meter or 10 pound inch. And the idea is that you like to tighten the screw such that there'll be good connection, so that there'll be good thermal transfer. On the other hand, it will be too tight and might crack the plastic and break it. So this is the mounting force, and this is for the two devices. And then finally we do have the weight of this device, just the bare device. So this will be the first part of the datasheet, maximum rating, and the next part will be also parameters, which are sort of test parameters, that not operational parameters, but they give some additional information and of the device. So let me go over it very quickly. We have the, again, breakdown voltage and what happens at the breakdown voltage. And then it turns out that the drain will start to conduct, and you might expect something like 3 milliamp when you reach 650 volts in the off condition, of course. This is the threshold. This is when the transistor starts to conduct. That is, below this value, the transistor does not conduct. Above it, start to conduct better and better. And normally in, say, switching system, of course, you like to be higher than that. In this case, it would like to at least 10 volts, maybe 15 volts. And it says that at this point, the drain might start like 8 milliamp. Obviously, you need much more in the power system. We're talking about a 120 amp device, okay? And then it says something about leakages, and that is the leakage, that is the current that you expect. DC current, DC, very important to understand that, because as far as the pulses go, the current is very heavy. We're talking about DC here, and it'll be like 50 microamp at 25 degrees, and it might go up to 5 milliamp at 125. By the way, in some blocks of the datasheet, some tables, you have test condition at the title here, which correspond to all the devices. You have to be very careful to look at it, because while it doesn't say anything else, like here, this means 25 degrees, because this is what it says in here, okay? And only if it says another temperature, then this will be corresponding to this value. And then we have RDS on for VGS 10 volt, okay, above, of course, the threshold. ID half the maximum, that is this 60 amp, because this is a 120 amp device. And this will be 24 milliohm. This is, the device is described as a resistor of 24 milliohm. Okay, and there's a note one here. It's very important to note the note, because in many cases this note do provide important information. In this case, maybe it's not, but let's have a look what it is. It will be at the bottom, of course. Here it says pulse test at 300 microsecond duty cycle. That is that specifying how this, where it is, how this value, this value here, how it was tested. Okay? Now, let me wrap up this first part here by saying something about resistances. Now, a MOSFET transistor, when it's on, it's like a resistor, and we call it RDS on. This is the resistance for the transistor. In this particular case, it's 250 milliohm, and for a 650 volt device, that's very nice. That's very nice. It's 120 amp. This is why 120 amp are allowed, because of the very low resistance. Now, let me mention the fact that these are MOSFET transistors, while we are actually now between the BJT transistors that have been used, and I'm talking now power electronics, they've been used in power electronics, but because there was nothing else. And now we move to MOSFET, but at the same time we have the IGBT, which is also based on a bipolar arrangement or construction, meaning that there is a junction, like a NPN. Okay, there's a junction here. And current is flowing through the junction. Now, the reason why MOSFET is ruling now, let me say that, is because there is no junction. When you have a junction, you have charge carriers, and therefore, when you turn it off, this device, you have to remove this. We'll talk about it later on in connection with the diode. You have to remove these charge carriers, and it takes time. So this is why IGBT is slower than MOSFET at turned off. You cannot turn it off very, very quickly, like a MOSFET. But there's another difference here, which is related to the question of RDS on. In the case of a transistor, of a MOSFET, if you are in the high VGS, this is VGS in our case, say 10 volt, and you look at the relationship between current and voltage around 0, this is a straight line, and as a matter of fact, it goes both ways. So the slope here corresponds to 24 milliohms. This is voltage over current, and it's bipolar. That is, you can pass positive or negative current, same way. The higher the current, the higher the voltage drop. On the other hand, in a BJT, very typical, you will see something like that. That is, this is voltage, and this is current, which means that you have such a, you start with a sort of a break point, and then this slope corresponds to very low resistance, and the voltage drop does not change much, the saturation voltage as it is called. And so IGBT will have typically something like that, while MOSFET, as I've said, will have something like that. And this brings about a very interesting point. If you're at a low current, say here, a MOSFET device will have a lower voltage drop. I'm talking about devices of the same structure and power ratings, etc. But if you go to very high current, like here, the voltage drop on the MOSFET will be higher than that of, say, IGBT. And this is why IGBT are preferred at very high current situation, like I'd say motor drive, where you might have very heavy current. I'm talking about hundreds of amps, okay? Because then the dissipation will be fairly low. I mean, relatively low because the voltage drop, Vsat, does not change much even as the current sort of climbs up. On the other hand, with a RDS-on, the voltage is proportional to the current. And as the current goes up, the voltage goes up. So this actually brings me to the end of this part 1. I do hope that you enjoyed this part here, and it was interesting, and that it will be useful to you. And hopefully I'll continue with part 2, going on with the next set of parameters of this particular transistor. Thank you very much.